Sorry about that. So let's go back. So like we agreed on last week, once I transform the systems of linear equation into a matrix form, okay, then I'm expected to have this form of transformation where you have one matrix putting together all the coefficients, another matrix putting together all the decision variables, and another matrix putting together all the resources. If I have this, because we agreed, can you see the screen now?
Yes. Yes.
Okay, great.
Yes, please.
Yes.
Great, thank you. So if the systems of linear equations can be transformed into a matrix form, therefore we are saying that in order to find the values for the decision variables, we can use a method called the Gauss-Jordan method. And what the Gauss-Jordan method requires that we use what we call ERO, elementary row operations, which will help us to find a way to transform one of the matrix into an identity matrix. Once we do an identity matrix, and we've also agreed that if I multiply any matrix by an identity matrix, I'm going to get the matrix itself. Last week we made that statement. So
yeah,
all we are interested in is to transform matrix A. That is the matrix that has all the coefficients into an identity what? Matrix by using this operation, elementary row operations. Once I do that, somebody
yours next.
Whoever you are, just mute yourself.
Will you be okay with it?
I need everyone to mute yourself until you have any question to ask, please. So you don't distract the class. Good. So the whole concern is that we have to transform matrix A, which has all the coefficients, into an identity matrix. And if we get the identity matrix times these variables will still give me what? The variable itself. So whatever is left with matrix B will be our solution. So note that at any given point in time that I'm transferring the set of elements in matrix A, at the same time, the set of elements in matrix B, which are the resources, are also changing. So you see that this B1, B2 to Bn will be transformed to K1, K2 to what? Kn. Then if an identity matrix of this time, this will give me the same identity matrix. Then we'll say that whatever is left with B, which is the element in the matrix B, will be equal to the decision variables values that I'm looking for. Thus, if we can transform matrix A into an identity matrix, then we have a solution for what? A times what? X, which is equal to what? B. In this case, A will be changed to what? An identity what? Matrix. Now let's see further explanation here. Okay, so as I said, we are using a methodology called the Gauss-Jordan method. And for the purpose of this class, we are not using any other technique to transform a matrix into an identity matrix except the Gauss-Jordan approach. I know there are other forms of approaches that you can use, but we are going to stick with the Gauss-Jordan method. And I need everybody to bear in mind. So if I'm giving you any problem to solve, you use the Gauss-Jordan method to solve for that problem. So how do we do the Gauss-Jordan method? We have elementary row operations. And by that, we say that it is ERO, the error of what? The matrices that we want to transform into a matrix and find a solution to the decision variables that we have. So an arrow transforms a given matrix A into a new matrix called A star via one or more combination of the following operations. And we are going to go through the operations in order to help us to remember when we're dealing with the matrix operation, we talk about scalar multiplication. So one of the elementary operation you can do by way of arrow is to multiply any row of a given matrix A by a non-zero scalar. So it can be positive or negative scalar, but not zero. We cannot use zero to multiply, zero as a scalar to multiply that. So you have to bear in mind which of the rows you want to do the operations on. So that if I have matrix A, and this is row 1, row 2, row 3, if I'm multiplying a scalar by a given row, then it is that row my interest is on, not any other row. So that if I'm multiplying row 2 of matrix A by the scalar 3, my new matrix, which will be A star, will be shown as below. Row 1 will still remain the same, row 3 will still remain the same. So I have 3, 1, 1, but 3 times 1, 3 times 1, 3 times 1 will give me 3, 3, 3. Then for row 3, it still remains as 4, 3, 1. What I have done is to do one of the operations. Then we can also look at addition, which we've discussed already, one of operation. Again, we are not adding all the elements in the matrix. We are adding a specific row by a given matrix, okay? Therefore, if I'm saying that by adding a row to another row, or by multiplying a row of A by a non-zero scalar and adding it to the row. So we can do both the multiplication and addition together. So if I'm saying that let's add row 3 of matrix A to row 1, we obtain, so I'm dealing with one of the row 1, but my operation is that I want to add row 3 of matrix A to row what? 1. Means that I'm adding 4 plus 3, 3 plus 1, 1 plus 2, but I'm trying to transform row 1. So my next matrix is going to be 7, 4, 2 in row A, in matrix A star for row 1. Row 2, row 3 remains the same. You cannot transform 2 rows or 3 rows at the same time. It is element row operations. So I pick a row and do my operations on. Or I can also say that let's multiply row 2 of matrix A by the scalar -2 and add to row 3. So I'm doing the same addition, multiplication together. I can also do division and addition together. I can do multiplication and subtraction together. So you can combine one or two of the operations, but you are only dealing with a row. So this is what we'll have here. So we're saying that we multiply row 2. This is row 2 of matrix A by -2 and add to row 3. But we are working on what? Row 3. That's my concern. This is what we want to do. So if I multiply row 2 by -2, I know this is -2, -2, -2. Okay. So 4 plus -2 will give you 2. 3 plus -2 will give you 1. 1 plus -2 will give you -1. I have only transformed row 3 by doing an error operation. Okay. We can go on and on. We can also do row interchange. Okay, instead of multiplying or adding, you want to begin your operation by saying that let me interchange a row by another row. Okay, remember the quest is to convert any given matrix into an identity form. And by identity, we said that all the elements on the diagonal section, they are 1. All other elements are 0. And identity matrix are square matrix. So this is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. So we are transforming this guy, the whole of this guy, into an identity what matrix. That is why we are using the arrow to find the decision variable x1, x2, and x3. That's all that the arrow or the Gauss-Jordan method approach suggests for us to be able to convert a given matrix into an identity what form. So we can do row interchange. So let's do, say, let's interchange row 1 and row 3. Okay, I'm moving the whole of row 3 to row 1 and bringing, this is not a transpose. I need you to understand that. Then I'm just bringing row 1 to what? Row 3 respectively. This is what that operation 2 says. So we'll pick a problem and see how we can use the Gauss-Jordan method with a combination of the operations to see how best we can transform that problem into an identity matrix form and also find a solution to the decision what variable. So if I have this problem, remember we have formulated already. So these are the equations that I have, and I want to find solution for x1, x2, x3. And I said you should use the identity form of this matrix A to compute the decision variable x1, x2. Then we are using what? The arrow. Okay. We can also use the arrow to do inverse of a matrix, to calculate the inverse of a matrix. We'll be coming there very soon. So please bear in mind, before we start the operation, all we are saying again is that we should find a way to transform these guys here, especially matrix A, into an identity matrix. Once I get an identity matrix, we know that an identity matrix times any given matrix will give you the matrix itself. So if I transform matrix A into an identity matrix I here, I know that when I multiply this guy here times x1, x2, x3, I'm still going to get x1, x2, x3. Then if that is so, as long as matrix B here, that's the raw materials have also changed to C1, C2, and C3, x1, x2, x3 will be equal to C1, C2, C3. What it means is that I need to find a way to augment the whole of this matrix here into one form, then go ahead to do my elementary row operation. So let's see how we go through it. Any questions so far, so we can proceed? Any questions so far? Okay, no question. Let's make progress. So this is a problem that we have, okay? We have this problem, and all we want to do is to transform by way of augmenting. I am moving, this is A and this is B. From what we have here, this is A and this is B. All I'm trying to do is that because there is nothing I can do in the quest of doing the operation to x1, x2, x3, I want to eliminate them first and bring matrix B closer to matrix A. So whatever operation I'm doing on matrix A, okay, that is the left distributive. Whatever I do, operations I do also affect matrix B. So you just say that the left-hand side is affected, the right-hand side must also what? Be affected. So that if I'm working on this row, I know if I'm transforming or I'm interchanging row 1 and row 3, that same operation must affect this row at the same time. So if this is row 1 and this is row 3, if I move row 3 to row 1 and row 1 to row 3, the whole of this row must come down to represent this one, and this one must go up there. That is what the augmentation says. So we augmented the whole matrix into 3, 1, 1, 1, 1, 1, 3, 3, 3, 4, 3, 1. Then I bring my small mark here to indicate that there is another row, another matrix called B. If I do any transformation here, it also affects this side. If I do any transformation in row 2, it affects row 2 in matrix B. If I do any operation here, it also affects the row 3 in matrix B. See, why is the arrow prefer to Cramer's rule? As I said, there are a lot of methodology. Gauss-Jordan method simplifies the entire operation and it's more modern. That's why we are using you can also use determinant rule to calculate the identity of a matrix or the inverse of a matrix. Cramer rule is the same thing, but we have adopted the Gauss-Jordan method. And for uniformity or conformity, I expect all of us to go alongside this method. Okay, the person who asked the question, I hope this simplifies or answers your problem. Okay, so from this, we can agree, okay, let's say if I augment this whole operation, then I can say that somebody will say, okay, let's work on row 1 or row 2 or row 3. And by doing that, we'll say that 3 times row 2 plus row 1. Okay, can you go over the augmentation? The augmentation is simple. Let me pick, let me come here, share a whiteboard. Okay, if I have 4x1 plus 3x2 plus x3 equals to 40, and I have x1 plus 2x2 plus x3 equals to 15, I have 3x1 plus 6x2 plus 4x3 equals to 35. I'm transforming these guys into a matrix form. We are saying that let's group all the coefficients at one side. So I have 4, 3, 1, 1, 2, 1, 3, 6, 4. We know this multiplies x1, x2, and x3 to be equal to 40, 15, and 35. Okay, we are saying that to perform the operation, technically, x1, x2, x3 are fixed terms, which we can't do anything to. We want to find the solutions for these guys here. So we just try to eliminate this guy here. So I'm going to have 4, 3, 1, 1, 2, 1, 3, 6, 4 equal to 40, 15, and 35, okay? Because we are performing the operations for these two, we say let's augment. By augmentation, we are just bringing matrix B closer to matrix A. 4, 3, 1, 1, 2, 1, 3, 6, 4. Then I have my 40, 15, and 35. This is augment. I've augmented this whole matrix into this form. Then I go ahead to use the Gauss-Jordan method, which is the elementary row operations. And that should be it for. Some people are redirected to a different meeting when they try to join the meeting using the link. Jackland, David, do you have a complaint from student?
I'm just hearing that. Let me check for the goodness.
I'm not sure there is another. Look, there are 3 groups. So if you don't belong to group 1 and you are using a different link to the group 1 link, you may be redirected to another one. So this, if you are not part of the group 1 meetings, group 2 met at 7:30 this morning. So this is group 1 meeting at 9:30. So whoever has challenge with the links, David, what you can do is to share the link to, I'm sure you guys have a platform. Try and share that link, our link to your.
Yes, I sent it.
You sent it to them. Okay,
evening,
those having
someone
challenge.
sent it again this morning, but it seems. Let me forward it again, please.
Okay, okay. So let's proceed. Let's proceed. Okay, so I'm just going to take you through a brief elementary row operation. Then we can go ahead to solve a problem using the arrows to arrive at the values for the decision variable. So like I said, I want to work on row 1 here. Means that I can multiply a scalar to a row and add to another row. But you have to exactly know which of the rows I'm performing my operations on. So if I want to change row 1, and I'm saying that the scalar 3 times row 2 plus row 1, it's allowed to do that operation. So 3 times 3, 3 times 1 is 3, plus 3 will give you 6 here. 3 times 1 again is 1, plus 1 will give you 4. 3 times 1 is 1, plus 3 times 1 is 1, plus 1 will give you 4. Then remember, you are also working on what? These particular matrices, because they are all on row 1. So 3 times 40, that will give you 120, plus 20 will give you 140. I have changed row 1. This kind of operation is allowed. Then I can also say that let's add rows together. So I'm working on row 2. Row 1 plus row 2. I'm using the new matrix. So 6 plus 1 is 7, 4 plus 1 is 5, 4 plus 1 is also 5. Then 140 plus 1 plus 40 should give you what? 180. We can also interchange rows. So this is my new row. I'm interchanging row 1, row 3. It's just to say that move the whole of row 3 to row 1 and the whole of row 1 to what? Row 3. That operation is also allowed. Let me see, some people are asking questions. Sir, please, isn't the scalar multiplying row 2 from 3 times? So you get 3, 3, 3, 4. Listen, we are saying we've combined 2 operations, okay? So 3 times row 2, we want to work on row 1. So 3 times row 2 plus row 1, we are only doing the operation in row 1. So it is not 3, 3, 3. It's 3 times 1 plus 3 will give you 6. Row 2 will still remain the same because the operation is on row 1. How do you know the scalar to use? When we start calculating the identity, trying to find the identity matrix, then we have to objectively look at what scalar to pick to help us to convert row 1 into 1, 0, 0. What scalar or what operation do we use to also change this row 2 here to 0, 1, 0? And what can we also do to change this row 3 here to 0, 0, 1? So it is not about choosing the scalar, but the information you have in the matrix and what operation to perform to aid in converting the whole of this into a matrix form. Sometimes you need to do about more than 4 operations to arrive at this solution, or you do like 6 or like 7 to do that, but you have to be smart about it. Otherwise, you'll be doing the elementary operation for as long as Jesus Christ will come, and you still not have a solution for the decision variable. So it is not about what kind of scalar do I choose? It is the element you have there and the operation you have to perform. So that answers your question, okay? I can also, like I said, we can also do row interchange.
Sir.
Yes.
Sir.
Yes.
Please, you mean if where the multiplication will be carried will be interchanged by where the addition will be done? So if I do the multiplication on maybe row 2 and the addition from row 1, meaning I'm going to exchange row 2 for row 1. For instance, the multiply row 2 by 3. So I've done it. Maybe 3 times 1 will give you 3.
So is that the operation you want to perform for that row? That's the question. If I just want to say, let's multiply row 2 by 3, then this will be changed to what? 3, 1, 1, 3, 3, 3, okay? 4, 3, 1.
Yes, please.
Then I have 1, this will be 20. I'll have 120 and I have 10. This in itself is an operation, but I just said that you can combine 2 operations. Instead of saying, let's multiply this, then you come and say, let's add this row 2 to what? Row 1 to give you this. You can combine 2 operations together. Does that answer you? Okay, sir, please, does it mean that this approach is subjective? Sir, please, what is subjective? If every methodology you use is subjective, sir, please, is it compulsory to interchange rows? I'm not saying it is compulsory. If the interchange can give you the solution you are looking for, then you go ahead to do the row interchange. Yes, David, your hand is up.
Yes, sir, please, this is about the meeting.
The meeting, yes.
We had a similar problem last week during one of our lectures, and we were told that it's a general problem occurrence. Some people couldn't join it.
Okay, so it's a general problem.
Yes, so now the only option is, now we have 2 options. Either we send a recording later for them to take it, or we end the meeting and rejoin again.
I should end the meeting.
It's 2 options. Either we continue this week. I think we are about 129
yes, I can't end the meeting. So
I believe we are more than those who want to join.
Yeah, so I will send them the recorded version.
Okay, so let me tell them.
Thank you very much.
Thank you.
All right, so my friend who asked the question, is it good now? The one who is asking whether this is even Kramer's rule has subjectivity. Identity matrix has subjectivity. Okay. So instead of paying attention, you are thinking about which of the methodology. Every methodology you apply has subjectivity. When you go to literature, you get this information with clarity. So let's make progress. Okay, so let's see. Now we pick a typical problem and let's find a solution to obtain the solution for the systems of linear equation. Like I said, continue to perform the arrows till you are getting this AX times B. Remember, A has been transformed into an identity matrix. So I'm still going to have A is transforming, B is transforming, X is still the same. So an identity matrix of A, I times X will still give me X. If that is so, then X is equal to what? K. That is until matrix A is transformed into an identity matrix. So let's have this example and go through and find a solution. We are using the identity form to find x1, x2, and x3. So given that 3x1 plus x2 plus x3 equals to 40, then x1 plus x2 plus x3 equals to 30. You have 4x1 plus 3x2 plus x3 equals to what? 60. That we transform that into a matrix form. So I have this transform into a matrix form, given that all the coefficient is represented in matrix A, the decision variable are represented in matrix X, and the resources are represented in matrix what? B. And as I said, we want to change matrix A into an identity form. And whilst we do this transformation, matrix B will also be changed to a given matrix called what? K. Then X will be equal to what? K. That is all the operations we want to do. So let me pick my whiteboard. Let's do some calculations here. Let me eliminate this one. Please, I need you to pay attention here. And whilst we solve it along, when your question pop up, I'll look at it and answer. If you also want to use a voice by way of talking, I'll pause and still speak to you as well, okay? At the end of the class, I'll send you the recorded version of the lecture so we can all have a fruitful discussion. So we have, as I said from the problem, we have 3x1 plus x2 plus x3 equals to 40. X1 plus 2, 3 equals to 30. And I have 4x1 plus 3x2 plus x3 equals to 60. And we say when we transform this into a matrix form, we should have 3, 1, 1, 1, 1, 1, 4, 3, 1, multiplying x1, x2, x3 equals to 40, 30, and 60, okay? And to augment this whole matrix, I'm going to have 3, 1, 1, 1, 1, 1, 4, 3, 1, and I'm going to have 40, 30, 60. Please note, we want to transform this guy here into 1, 0, 0, 0, 1, 0, 0, 0, 1. That is the whole discussion that we're going to have, okay? So what can we do? This guy must change to 1. This guy should be 0, 0, okay? This guy must be 0. This should be 1. This should be 0. This guy should be 4, should be 0. 3 should be 0. 1 is still what? 1. So think through. Which of the rows should we work first? And what kind of operation can we do? Okay? Any suggestion? I'm trying to have a participatory class and not a class that just solves the problem. And I know you have the slides, so don't worry yourself to go through the slides once I'm teaching. I need you to understand the whole concept. All right, so any suggestion? Remember, these guys are here. We have 3, 1, 1. This is row 1, 1, 1. Yes, somebody is talking. What do you have in mind? Which row should we perform on? We can start with row 1. Okay, so what can we do on row 1? Okay, so let's say row 1 minus row 2. Okay, let's try this. Row 1 minus row 2. So 3 minus 1 will give you what? 2. 1 minus 1 will give you 0. 1 minus 1 will give you 0. This is what? 40 minus 30 will give you what? 10. So I still have 1, 1, 1, 4, 3, 1. This is 30 and what? 60. At least I've transformed or I've changed these elements, so I know I don't have to work on this element in row 1 again. 0, 0, 0. They are 0, 0. All I need to do is to get what? 1 here. Then I can say row 1 is 1, 0, 0. Is that okay? Hello, guys.
Yes, please.
Okay.
Yes, please.
What operation can we perform again?
Yes, please.
Okay. What operation? Think through. Now, I need to ensure I can leave row 1 and come to row 2 to work on. You don't have to stick to a particular row because you need to change it. As a matter of fact, another row's transformation can help you to solve or find a solution for another row that you are looking for. So what operation can we perform now? Think through.
Okay. Please let's divide row 1 by 2.
You want us to still work on row what? 1.
Row 1.
So row 1 divided by 2. Yes, division operation is also accepted in arrow. But you can't say let's divide row 1 by 0. Non-zero scalar. Only non-zero scalar. Okay, so let's look at what our friend said. So 2 divided by 2 is 1. 0 divided by 2 is 0. 0 divided by 2 is 0. Okay, then I have 10 divided by 2 is what? 5. Row 2 is still the same. Row 3 is still the same. And I have 30 and what? 60. That's what we have done.
60.
So at least row 1. Question, yes.
I raised my hand, but I think you didn't see.
Okay, please go on.
You see, we are working on the rows. Is it possible that like you can work on the column?
No. It is elementary row operations. We don't work on columns. We work on rows. When we're doing a matrix operation, this was a statement I made. You work on rows, not columns. Please.
Yes.
Yes.
Yes, thank you.
You're welcome. So row 1 is okay. We are left with row 2 and row 3. Row 2 looks simple. All we need to do is to make sure this is 0, this is 0, this is 1. So who can help us? Or you want us to also work on row 3? It's also agreed on. 3 hands are up. Yes, those hands up, you can talk. The remaining ones, mute your videos. Godfred.
Okay, sir. Please, I think for the row 2, we can make it row 2 minus row 1.
Row 2, so we should work on row 2. So row 2 minus row 1. Let's see. Row 2 minus row 1. So we know row 1 is still the same, which is giving us, this is still 1, 0, 0. And you have a value of what? 5 sitting somewhere. So we are working on row 2. So 1 minus 1 is 0. Okay? Is 0. 1 minus 0 is what? 1. Then 1 minus 0 again is what? 1. 30 minus 5 is 25. Row 3 is still the same. 4, 3, 1. And this is what? 60. Okay. Which row again can we work on? Which row?
The last row.
Row 3.
The right side.
Yes.
But here is 1.
Enim danso. Yes. Any question, guys? Okay, so we'll say let's work on row. Still, we want to look at, instead of working on row 2, if we keep working on row 2, we may get a solution, but that will take us longer. So others will say that let's look at row 3. What can we do on row 3? Okay, remember we have here 0, 1, 1, and we have 4, 3, 1. What can we do to make sure the 4 is 0, the 3 is also what? 0. What can we do? Yes, Richie, your hand is up. Please go ahead.
Okay, so for the row 3, I think we can multiply row 3 by row 2 so that we get the 4 as 0.
We should multiply row, go on, row what?
3 by 3 by
row
row 2.
3
By row 2.
Okay, so you cannot multiply row by a row. You can multiply a scalar. Remember, when we're doing the operation, we only said you multiply a row by a scalar. You can add rows together, subtract rows together, but you cannot multiply rows together. Richie, I hope that explains. It looks good, but we cannot multiply that. Richie, is your hand up again? Okay, Mario.
No,
Mario.
Yes, sir. Please, we can operate. We are operating on row 3.
Row 3, yes.
So, row 3 minus 4 times row 1. Then that will get rid of the 4 in row 3.
Row 3 minus what?
4 times row 1.
4 times row 1. Are you sure you are not giving me solution to my
Oh, no, sir.
I want you guys to think through before, you see, don't be focused on my solution. Otherwise, I'll just do that and leave you. Okay, so let's do this. We are working on row 3. Mario said we should look at 4 times row 1 minus what? Row 3. So 4 times 1 here, this will be 1, this is 0, this is 0. I have here 5, okay? So 4 times, row 2 is still the same, 0, 1, 1. Let me copy that one. Okay, so 4 times 1 is 4. Then 4 minus 4 is 0. 4 times 0 is 0. 3 minus 0 is 3. 4 times 0 here again is what? 0. 1 minus 0 is what? 1. 4 times 5 is, that should give you 20. 60 minus 20 should give you what? 40. So yes, that operation is also agreed on. Let's do that. Can we add row 1 plus row 3? Yes, we can do it, Francis, but which row do you want us to do the addition? You need to tell us the row we can do the addition, then we can try that one to see. Okay, so let's make progress. What row again can we work on?
So we can work on row 3 again.
We should still work on row 3. Okay, so let me come here, row 3. What operation are we doing on row 3?
Let's multiply row 2 by 3 and subtract row 3 from it.
We should subtract row 3 from
2
times
3 times
3 times row
2.
Okay, so I should do 3 times row 2 minus row 3. Is that it?
Yes.
Okay, we will do it, but I'll show you what will happen. Always check through which of the resources has the greatest value. Sometimes the operation is correct, but you end up getting negatives throughout. Okay, so this one, 3 times, watch here, row 2 has 25, okay? So 3 times, is it 3? Yeah, 3 times row 2 minus what? Row 3, okay. Then let's just do it and see what will happen. Okay, so 1, 0, 0. Here we have 5. Row 2 is still the same, so 0, 1, 1, and I have 25. Okay, so let's go on. 3 times 0 is what? 0. 0 minus 0 is 0. Okay, 3 times 1 is what? 3. Right? And 3 minus 3 is also what? 0. Here again, we have 3 times what? 1, that's 3. 3 minus 1 will give you what? 2. Okay. Then we have what? 3 times what? 25. That gives you 75, right?
Yes.
So 75 minus 40 is what?
35.
35. Okay, I think I like this. That's good. Sometimes what I wanted to say is sometimes you may end up getting all negatives and you have to divide the row by a negative scalar so you can try to avoid the negative. What should we do next?
Okay, so to proceed, I think we should divide row 3 by 2.
So all this while we are working on row 3. Guys, sometimes that's what you have to do. You have to finish a row before you can work, or that row can help you do or find solution for another row. Yes, somebody want to ask me a question. Go ahead. Always check through. I didn't get that part.
Minus root and divided by 2.
Say that again. Yes. Whoever is talking, Eunice, we can't hear you clearly, so speak louder.
Sir, please, row 3 divided by 2.
Row 3 divided by 2. Somebody too said row 3 times 0.5. I don't know what. Wow, that's a smart choice, but sorry. So row 3 again, but we are saying that row 3 divided by 2. This is straightforward. 1, 0, 0. I have here 5. 0, 1, 1, 25. So 0 divided by 2, 0. 0 divided by 2, 0. 2 divided by 2 is what? 1. 35 divided by 2 will give you 17.5. So at least we've dealt with row 1 and row 3. We are left with row 2. This guy here should be 0.
Yes, yes.
So what can we do?
Row 2 minus row 3.
Row 2 minus row 3. I have here 1, 0, 0. This is 5. Then I have 0, 0, 1, which is 17.5. Row 2 minus row 3. 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is what? 0. 25 minus 17.5 should give you 7.5. Okay. So technically, how many operations have we done? If I may want to count, we've done 1, 2, 3, 4, 5, 6, 7 operations to arrive at this. So we have converted matrix A into an identity what? Form. And we have also converted matrix B, which is the resources, into what? K. So I can rewrite this whole thing and say that what I have here should be 1, 0, 0, 0, 1, 0, 0, 0, 1 times what? X1, X2, X3 equals to 5, 7.5, and what? 17.5. We know this is an identity matrix, which multiply X should give me what? X. Therefore, X is equal to what? 5, 7.5, 17.5. If I do that, I can now conclude per what I have here to say that what COVID has done to us. Restricted. Okay, so I can now say that X1, X2, X3 equals to 5, 7.5, 17.5. Therefore, X1 equals to 5, X2 equals to 7.5, X3 equals to 17.5. That's my solution. So we have only used the arrow to determine the identity matrix of that systems of linear equation to find X1, X2, and what? X3. Any question, please?
Sir.
Yes.
Yeah, please. Are we supposed to, let's say I'm solving a question for you. Do I have to write the rules? Are you supposed to write the rules, the R3 equals?
Of course,
R2.
you have to. We need to know we need to know what you are doing. Okay, so that if you are performing a magic, we'll follow your magical process. Like somebody says that we should multiply a row by another row. You can do that operation, but that is not accepted with the arrow. All right, Seth, please go on. Seth, you are asking a question.
For the resource side, sir, please, for the resource, can you get a negative figure or 0?
Okay, so along the line, we will agree that you can't have a negative value for a decision variable. Okay, therefore, like I'm producing, and the question is on production, or you are making a decision on what kind of, how many acres of land to allocate to a given decision variables. You cannot have negative land to allocate. So along the line, if any of these values, 5, 7.5, 17.5 is negative, you need to go back to check. They can either be 0 or non-zero number. Please note that 0 or non-zero. You can't have a negative value. So does it mean my attempt to turn matrix A into an identity matrix, I can use any means possible? Are there any rules we should follow when we are trying to obtain? Yes, if you say any means possible, every mean is possible, but I'm saying that the arrow do not allow you to multiply a 0 to any row. Please note that. You cannot also not multiply 2 rows together. Apart from that, you can do any of the operation. But if you are not careful and you are just choosing numbers or choosing rows and rows to do that, you may end up solving the question till Jesus Christ comes. So just pay attention to the solution you yourself want to attain. Any questions so I can go ahead to?
Yes, please. Sir, please, a question.
Yes.
There's one particular operation that I don't know if it's possible we can look at it again.
Okay, tell me.
Date row 3 was equal to row 3 minus 4 row 1. From there,
minus 4 row 1. Yes, this one.
Yeah, I think from here we moved on to another one, which was the row 3 is equal to 3 row 2 minus
row 3.
And row 3. Yes, please. Can you look at that particular operation in the 3 row 2 minus the row 3? The answer
okay, so this is where we were. We were here. 1 0 0 5. Then we said that let's work on row 3 again. So 3 times row 2. Okay. 3 times 0 is 0. Is that okay? Then 0 minus 0 will give you what? 0. 3 times 1 here is 3. 3 minus 3 will give you what? 0. 3 times 1 is 3. 3 times 1 is 3. 3 minus 1 is what? 2. 3 times 25, we said 75. 75 minus 40 will give you 35. Is that explainable?
Yes, please. Yes,
is it clear?
Yes, please. It's clear now.
Okay. Godfred, please go ahead and ask your question.
I'm the one who just asked the question.
Oh, okay. So that's fine then. I'm taking a few questions, then we can go on. If you have any question, please ask quickly so I can move on. Any other question, please go on so that I can. Okay, I presume we don't have any. Yes. Yes, go on. Please go on with your question.
Yes, sir. All right, sir, please, someone asked a question whether the final solution can be 0.
I said yes. A decision variable solution can be 0. We are saying that they are either 0 or positive, but they cannot be negative because I cannot allocate negative land for production. Is it clear? All right,
yes,
so
please.
okay.
Thank you.
You're welcome. This should be simple for everyone to go through. It shouldn't be a problem. Okay. I said, no, you can't. Sir, you said you use a non-zero scalar. Oh, why are you confusing yourself? A non-zero scalar can multiply row operation. The question the gentleman asks is, can you have a negative value for the x1, x2, x3? And I said no. Provided you go through operation correctly and the matrix becomes an identity matrix, the answer will be correct. Okay, that's the next hint I'm going to give you. Maureen, if you finish with this and you have this solution, what you can do is to substitute x1 value, x2 value, x3 value into the equation to ensure that when you multiply and add, will you get 40? Will you get 30? Will you get 60? That's what you can do. Okay, Maureen, that's fine. So always remember, sir, please, if you get a decimal, can we round up? Guys, these are not questions you should be asking. If you get a decimal, will you round up? All right, so apart from this, we can also use what we call the same operation to calculate. Let me pick another question. I'm trying to pick another question so we can use, okay? So let's see this. Let's look at this problem, okay? One more question on the identity. Then, sir, please, in the quest to find the identity of a matrix, is there the need to ensure also that x1, x2, x3 values are kept in their lowest term? It is the problem that you have that you should be mindful of, Daniel. In the lowest terms, oh my good friends. Okay, so let me pick another example quickly and we'll go through, okay? I think that should help our problem. And this one is just a free question I'm picking, so we will all solve it together. Then I can go to the next, using the inverse of the matrix. We can also do another operation. Instead of using the identity matrix, we can use the arrow to solve for a given what matrix. So let me take this example. Clear all drawings, okay. All right. Say, can you add or subtract a row to a number? For instance, row 1 minus. Did we do this operation the last time? We said we can only multiply a scalar to a given row. Please, guys. What do you call it? Doing voodoo calculation. So let's say we have 2x1 plus x3 plus x3. No, I want to pick a simple problem. Let me increase the values because some of you. Okay, so I have 20x1 plus 2x2 plus 10x3 equals to 400. Then I have x1 plus 2x2 plus x3 equals to 40. I have x3 equals to 5. Okay, so let's say this is you have a problem, you formulate the systems of linear equation. By way of augmenting, we know I'm going to have what? 20, 15, 10, okay? Times x1, x2, x3 will be equal to 400, 40, and 5. This should give me x1, 2, then X1 here. I have 0, 0, 1. Augmentation, I should have 20, 15, 10, 400, 1, 2, 1, 40, 0, 0, 1, and 5. Okay. Let's make progress. So based on this, what can we do first? Can anybody suggest? Maureen, yes.
First start by dividing row 1 by 5.
Okay, so so you want us to work on row 1. I will say row 1 divided by 5. Yes, you can do division, it's allowed. Okay, so Maureen, if we should do what you are suggesting, this should give us what? 4, 3, 2. And this will give us what? 80, right? Then 1, 2, 1, 40. Then you have 0, 0, 1. Okay, and 5. Okay, I like it. What operation can we perform again?
Step is row 2 minus 1.
Row 2.
Row 2.
Row 2. We should work on what row?
Row 2.
Row 2.
Row 2 minus.
Row 2 minus row.
Minus 1.
We cannot do row 2 minus 1. I was just explaining that to you. You cannot subtract a scalar from a row. You can only multiply a row or divide a row by a scalar. Is that okay?
Row 2 minus row 3.
Row 2 minus row 3. Row
yes,
2
that's what you say.
Minus row 3. Is that it? We are working on which row?
Row 2.
I'm working on row 2.
Row 2, okay. Row 2. So row 1 is still the same, 4, 3, 2, 80, 40, and sorry, this will not be 40. So row 3 minus row 2 minus row 3. So 1 minus 0 is 1, 2 minus 0 is 2, 1 minus 1 is 0, 40 minus 5 is 35. Then you have 0, 0, 1, 5. Okay. What can we do again?
Let's do row 1 minus
Please
3
don't
times.
be doing jackpot or cha-cha here, okay?
No, it's not jackpot. I want to you see the how do you call it? The A13, the 2 there. I want us to change it to 0, okay?
Which one? This guy here.
On row 1. Row 1, column 3.
On row 1.
Column 3. The 2 up there.
We are not dealing with column. We are dealing with rows. So
yeah. I'm giving you the position of the number.
Mm-hmm.
So row 1, column 3.
Row 1, column 3. This guy here too.
Yeah.
Mm-hmm. What should we do?
So we are going to work on row 1. So here we multiply row 3 by 2 and sub. So it will be row 1 minus 2 times row 3.
This is the operation you want us to do. We are working on row 1. Okay, let's see. So 2 times row 3 here, this is 0. You are only going to change whatever operations you do, try and change one or two, more than one element. If you keep changing only one element, you end up doing more process. Is that okay?
Yes.
So it looks okay.
Sir, please, how about we interchange row 2 and row 1 and row 2?
We interchange
row 1 and row 2.
Okay, so let's hold on to this suggestion first. Okay, we'll come back to that. So let's interchange row 2 and row 1. Is that what you said? Hello?
Yes, please.
Okay, so now I have 1, 2,
yes, please.
0. Then I have what? 35 here. This will be 4, 3, 2, 80, 0, 0, 1, and 5. I want to understand the reason behind this. Why do we do this interchange? Why the interchange?
Because I'm trying to aim at the diagonal, the ones.
Okay. So now you have 1, 3, 1. Okay, so what should we do again? Guys, I can solve this within the shortest possible time, but I need you to participate. What should we do?
Okay, sir, please, we are working on row 2.
This is not a transpose. Somebody is asking, we are not dealing with transpose. It's interchange. Transpose is different from interchange. I explained it earlier. Okay, yes, my friend, go on.
Okay, sir, please, we are working on row 2.
Row 2, okay.
We subtract row 1 from row 2.
Row 1 minus row 2. Is that it?
No.
Row 2 minus row 1.
Yes, please.
Okay, so let's see. Row 1 is still 1, 2, 0. Then you have 35. This will be what? Row 1.
Row 2. Row 2 minus row 1.
Okay, so what do we have? 4 minus 1 will be 3.
3, yeah.
3 minus 2 will be 1.
1.
2 minus 0 is 2. 80
yes.
minus 35 should give you what?
Should give you
45.
45.
45.
You still have 0, 0, 1,
0,
and
1.
what? 5. Okay,
5.
This looks interesting. At least diagonals are working. Okay, what should we do next? We are left with 3 elements to convert. This, and that guy. What should we do next?
Okay, so I think we can multiply row 3. Here, since it's 3, I don't think we can get 2 at the same time. So let's multiply row 3 by 2 and subtract it from row 2.
So 3 row 2 minus row what?
No, 2 is 2 row 2. 2 row 3.
Row 3.
2 row 3, yeah.
Minus row.
No, say it's row 2 minus 2 row 3.
No, it's supposed to be, yeah,
row
sure.
2 minus 2 row 3. To give us row 2.
I should do what? Tell me.
So row 2, R2 minus 2, R3.
R2 minus R3.
No, 2 R3.
Okay, this one.
Should give us row 2.
To give you what?
Row 2.
1, we are looking at row 2. So yes. 1, 2, 0. Okay. 35. We are working on row 2. Those of you who are not contributing, I hope you are just following. Okay, so 2 times
0 is 0.
0 is 0. 3 minus, but you still get the same thing.
Yeah, no, we will be changing
3,
the 2.
Okay, so 3 times 0, 1 minus 0 is 1. 2 times what?
1 is 2.
And okay, so 2 minus 2 is 0. 2 times 3 is 5 is what? 15. 10. Is that it? So 45 minus 15 should give you what?
No, it says 2 times 5, that's 10.
Oh, this is 5.
2 times
2 times 5. Yes. Okay, so then 45 minus 10 should give you 35. Okay. Okay, that makes sense. This is still 0, 0, 1. Okay, so smart choice, but you have a bigger task. What should we do next? Now you are left with which element? 2 elements. So what should we do next? Somebody should. Any suggestion, guys?
I don't know. Okay, let me see. Let's see whether we can change the 2 up there.
We should change these 2 up there. Why not change the 3?
Okay, like 3 rather. Okay. So if that, then we multiply row 1 by 3.
So let's say we are going to do 3 row 1 minus what? Row 2. We are still working on row 2. Okay, let's I think I'm wasting time on it. Let me help you do this quickly. Let's go. So this should be 1, 2, 0, right? Yes, so 35. Okay, 3 times 1 is what? 3. 3 minus 3 is what? 0. 3 times this guy will give you 6. 6 minus 1 will give you 5. 3 times 0 is 0. 0 minus 0 is what? 0. 3 times 35 is what?
105. 105, yeah.
105 minus 35 should give you what? 70, right?
Yes.
This should be 0, 0, 1. This is still 5. Okay. Next thing to do, if we have this, all we can do is to say, let's work on row what? 2. And we say row 2 divided by 5. All right? So this will be 1, 2, 0. I have here 35. This should be 0, 1, 0. This should give me what? Back to what? 70. That should give me 14. Yes. Then I have 0, 0, 1. Then I have here 5. What can I do next in simple terms? Can anybody help?
Okay. Let's multiply row 2 by 2. Row 2 by 2. So it's to get okay. Yeah, row 2 by 2.
So what?
So also we can row
1 minus
row 1
minus 2 row what?
Row 2.
2 row
2.
2 row 2. Okay. What do we have? 2 row 2. Remember, this is 2 row 2. So 2 times 0 is what? 0. 1 minus 0 is 1. 2 times 1
is 2.
2 minus 2 is what? 0.
0.
2 times 0, 0 minus 0 is 0, okay? Then this will give you 7. 2 times this guy here.
14, 28.
Minus 35 minus that should give you 14. To give you 7, sorry. Then I have 0, 1, 0. I still have 14 here. Then I should have what? 0, 0, 1, and that should give me what? 5. So technically x1 is 7, x2 is what? 14, x3 is what? 5. You can substitute this guy 7, 14 respectively into this equation to find out if you are getting 440 and what? 5. So this is just an identity form. How many did we do? I'm just helping you to see how you can make your work shorten. 1, 2, 3, 4, 5, 6, 7, 8. We could have done 7 steps or 6 steps, but I'm happy you suggested all the steps throughout. Anybody having any question, please ask me. Then I introduce you to the next.
Sir, please, I have a question.
Yes, go on.
Sir, please, you see, we did some interchange here. We interchanged the row.
We did interchange row 1 and row 2.
Yes, please. Yes, please.
Here, this one.
So, please, I wanted to ask, won't it affect the final answer because of the interchange?
No, the interchange do not affect the final answer. It is the process you are going through to get the final answer. So even here, look here. If when we got to this point, this side 1, 2, 0, 35, and we feel we can interchange a row to get a solution, it's allowed. All you need to do is that's why I'm saying when you get your solution, substitute the x1 values, x2 values, x3 values into the original operation, equation, to see if you'll be getting the final answers. I'm sure you
did. You have the you had the final answer. I did that on this.
You did it. Fine. Fantastic. Okay. So let's make progress. Last question, then we can proceed. Sir, please, can you mention all the operations that are unacceptable when finding the identity matrix? One last time. I said you cannot subtract a scalar from a row. We can also not do multiply 0 as a scalar to any row. I think basically those are the two main things you can, but you can add row to another row. You can subtract a row from another row. I need you to, but you can also not multiply row by a row. Let's multiply row 2 by row 3. We can't do that. We can multiply a row by a scalar to find the solution that we seek. Okay, my friend.
Sir.
Let me go back to my slides.
Sir.
Yes.
Yeah, please, with the division, to be on the safer side, why don't you say that instead of dividing directly, we just say, okay, you multiply by the inverse of what you want to divide with. So if
please,
you want to divide
I don't
by
want
5,
to confuse the entire class.
Okay.
We are all not at your level, okay? Others are still struggling to understand. So I'm just saying that divide a scalar by a row. Is that okay?
Yes, sir.
Don't let us confuse our other friends. Can you divide a row by Angela? We cannot use the scalar 0. We can use positive and negative scalars to divide or multiply a row. Angela, I hope that is clear, if you can hear me clearly. Don't use 0 as a scalar to multiply any row or divide any row. All right, let's make progress. We've gone through. Then we can also see how to use the inverse of a matrix to find our solution. And I hope you remember this rule here. Then we say that for a given matrix that multiplied its inverse, it should give you an identity what? Matrix. Therefore, suppose B is any matrix that satisfies this problem that we are looking for. So please, if we want to find the results for say row 2, can we do an operation like 3 minus row 2? How do you do 3 minus row 2? For that particular row 2, I just said that you can't pick a scalar and subtract it. Guys, stop asking questions that will not stimulate.
It was like, say it was row 3 minus row 2. Not like 3, it was row 3 minus row 2.
You can subtract a row from another row. I said you can do that, just as you are adding a row to another row, okay? Yeah. So suppose we have this, the inverse of A times A B is equal to the inverse of A times what? The identity matrix. We know an inverse of a matrix times a given matrix will give you an identity matrix. So this will be converted to this identity matrix multiplied by what? B. And we also know that if I multiply an identity matrix to any given matrix, which has the same characteristics, I should get the matrix itself. So B will be equal to the inverse of what? A in this problem. That means that B must be the inverse of A. Because of this, we can apply the Gauss-Jordan method to find the solution. So please note that for a given matrix, and want to find the inverse of that matrix, the operations of arrow is the same. So that if we say let A be an invertible matrix, then the inverse of A can be obtained through the Gauss-Jordan method. Step 1, formulate or form the augmented matrix. Then the next step says that transform A into what? This guy and that. The resulting matrix B is the inverse of what? A. Please look at this. If I have this matrix, this time around, I'm not finding the identity matrix for A. I want to find the inverse of A. Okay? The same operation says that once I know this, I can find the identity matrix. This is a square matrix. I can represent this into an identity matrix and perform my operation. So this will be 1, 0, 0, 1. Okay. Then what do? I use arrow. Arrow means that I'm now transforming A into an identity. As long as I'm transforming A into an identity matrix, I A will be changed into the inverse of what? A. That's all this is trying to explain. Okay, so the problem here is now, as long as you are transforming A, remember it is an arrow operation. This will be your row 1, this will be your row 2. Whatever operation I'm doing on A is also affecting what? The identity of that particular what? Matrix. So watch here. In simple terms, this is 2, 4, 1, 0. The identity of 2, 4, 1, 0 is 1, 0, 0, 1. We said the first operation is to divide row 1 by what? 2. Row 1 by 2 should give you 1, 2. This will be 1 over 2. This is 0. The next operation, we are saying let's subtract row 1 from row 2, working on row 2. Okay. This is 1, 2. This will give you 1 minus 2. Whatever I'm doing here is affecting this guy here. Similarly, if I come to 1, 2, and 0 minus 2, all that I have done, just to conclude this, is to get what? The inverse of A. So the original matrix, which is 2, 4, and 1, 0, has been transformed into what? The inverse of what? This one. Then, if I have the inverse of this, and I have the resource factor to this operation, I'm going to multiply the inverse of A times, so let's say I have 40 and 30 here from the given problem. This minus what? 0, 1, 1 over 4 minus 1 over 2. And that should give me the solution that I seek. Please, what does finding the inverse means? We are borrowing an applied methodology to find the solution for the decision variable. That is what we are looking at. Okay, so so let's say we have this as a problem, okay? And I'm asking you to find this is the systems of linear equation. We want to find P1, P2, P3. And instead of using the identity form of a matrix, I said, find the inverse of what? A. If I transform this into this, I said, find the inverse of A. What you go through is the same arrow. But now we will write the identity for A, giving us this 2, 4, 8, 5, 7, 0, 8, 12, and 2. 1, 0, 0, 0, 1, 0, 0, 0, 1. Once I'm transforming here, it also affects here. The solution you see here is as a result of the transforming this into an identity what matrix 0, 1, 0, 0, 0, 1. Then this guy here is what has been transformed to this side. When I get this, I have to multiply this whole by matrix B to give me P1, P2, P3. Okay, so what we should bear in mind is that if we formulate a system of linear equation, and we want to find the results for the decision variables, one of the key techniques we can use is to use what? Matrix. And by matrix, we say we can use the Gauss-Jordan method to find a solution for our decision what? Variable. Another methodology we can use is the graphical method. Okay, I'm coming to explain the graphical method very soon. We can also use Excel to perform all the operation. Next week, I'll take time to use the Excel, teach you how to use Excel to solve matrix problem, okay? But what we want to do next is to go to what we call linear inequalities. Remember, we were saying that the equation is equal to a certain number, that is the resources. But technically, in a real world problem, you may not have all problems in the form of what? Equality. Given that if I have something to consume, or if I have money to distribute, as a finance manager, because I want to save some money down, in the course of distributing so and so amount, I have to ensure that there is some amount left for future expenditure. Therefore, we will say that your total resource you have may not always be the case that you have to share everything. And that's why we are introducing you to the systems of linear inequalities. By linear inequality, our resource value may either be less than or equal to, or greater than or what? Equal to. Therefore, we need to understand that if we are writing any linear equation, we have to pay attention to how the resource is to be what? Allocated, or how the resource is to be what? Distributed. Please note that. So that there are some statements that we need to bear in mind. For example, watch here. If a household has 300 on rice and soda drinks, a bag of rice costs 20, and a pack, we've solved this problem already, but the statement is saying you should write a relation detailing how the available 300 Ghana cedis is spent. How the available, if you have an available amount to spend, okay, the possible way to spend that money is either you are spending everything or you spend less of that. So the word available means that it is less than or what? Equal to. If you go to the shopping mall to spend or to shop for some items, given some amount of money that you have, I am sure you know you cannot spend more than what you have in your pocket, but you can spend less of what you have in your pocket or spend exactly what you have in your pocket. So there are two ways, either less than or what? Equal to. So when I'm writing this equation, after I've defined my decision variables, at this juncture, we all know how to define our decision variable. Therefore, this will not be equal to anymore. Oh. Where was it? Okay, so this is no more equal to, but it's inequality, it's non-equal. So we said that the available amount is to spend or spend less of that. Let's solve this problem. Are you with me, guys? Hello?
Yes, please. Yes, please.
You are silent. And so let's go through this. An investor has 1 million to invest in 3 assets. The annual market returns of the assets are 10%, 13%, and 12% respectively for asset 1, asset 2, and asset 3. To avoid market risk, the investor has been advised that amount invested in assets 2 and 3 must not exceed 650. How much should be invested in each asset? The investor wishes to realize a total income of at least 6% of the total annual amount invested, and assume 1 million must be fully what? Spent. So we need to formulate the problem for this. Formulate or transform all these into a linear equation form. Can we identify the decision variables quickly? How many decision variables do we have here? How many decision variables? 3, okay. What are they?
Asset 1.
Asset 2, asset 3.
And 3.
Okay, so let's now define the decision variables. Now that we know them, let's define them. How do we define them? Let x1 be what?
Asset 1.
Let x1 be
Asset 1.
You are all wrong.
And now
The value.
Remember, we always say that there is something to make a decision, not the decision itself.
Let S1 be the amount to be invested in asset 1.
Perfect. So it is not that let x1 be asset 1. Let x1 be the amount to invest in asset 1, respectively to amount to invest in asset 2, amount to invest in asset 3. Then the first statement is that the annual market returns of the assets are 10%, 13%, and 12%. And we are also told that the investor is to realize a total annual income of what? 6% of the total amount invested. And that we can also invest all the amount in asset 1, asset 2, asset 3. So this is our decision variable. We can invest all the amount, means that x1 plus x2 plus x3 is equal to what? 1 million. We are told that asset 1, we can have invest, the amount we invested in assets 2 and 3 must not exceed. Must not exceed means you cannot go above what? 650,000. You can either invest below or you can invest the exact amount. That's why we have this statement here. X1 plus X2 is less than or equal to 650,000. We are also told that the annual income we are expected is at least 6%. At least means that you cannot go below, but it is either the same amount or more than that amount. Asset 1 is 10%, so that's 0.1x1. Asset 2 is what? 13%, 0.313x2. This is 0.1x2, x3. At least is greater than or equal to what? 6% of the total annual what? Income. This is what we have done. So it's just to, again, bring to your notice that you may have equality sign in your equation or inequality sign in your what? Equation, which can be less than or equal to or greater than or equal to. Eunice, can you kindly mute your microphone? You are disturbing us. Thank you. Let me see if anyone. Okay, everybody is on Eunice. All right, so let's look at this last one. I'm only trying to show you inequalities before we solve any problem, okay? A household has 4, we've also gone through this already. So, but this time around, let's look at the first constraint, the 300 here. We are told that in addition, the household should spend at least 300 on rice, on soda, and on what? At least 300. Remember I said at least is what? Greater than or what? Equal to. And we are told that 20 for rice, a bag of rice will sell for 20. A pack of soda drinks will sell for 15. And a bar of soap is what? 10. So 20x1 plus 15x2 plus 10x3 is at least greater than or equal to 300. 400 is to be spent on soda drinks and all that. What we have is the available amount we have to what? Spend. We are also told that assume the household has No, write a relation to say it's spent on 2 items and show the relation. This is this one, and that is this one. So we are here trying to find this. We are told that we are to buy at least exactly 5 bars of what? So at least in this case means that greater than or what? Equal to. I need you to. What about at most? At most is what? If I said I have
less or
Less than or equal to.
less than or equal to. So I have 17 mangoes, and I say you can eat at most 10 of the mangoes. At most 10 means that you can't exceed 10 mangoes. You should just eat something below or exactly what 10 what mangoes. So pay attention to the at most. And the last one we've also gone through this time around is what? Equality sign. So my good friends, if we are able to do this, if we want to again find a solution for x1, x2, and x3, remember we said one of the technique we can use is matrix. The other technique we can also use is graph. We can use graphs to also find the value for what? The decision variables. But if we are using graph, remember we can only deal with 2 decision variables when we are using with graph, because usually graphs have the x and y what? Axis. Therefore, if this is x1 and this is x2, if I want to use the graphical method to calculate or find my decision variable, then that problem should have only 2 decision variables. If you have more than 2, graphing systems cannot help us find a solution to the problem. So the next is to use graphs. I know our time is getting close, but we're going to go through the graph quickly. Then the next week, we can look at other methods as well to find that. So if I write this as my set of linear equation and want to find x1 and x2, what graph says that I need coordinates to find my solution. So let me go through the graph quickly, which is the easiest form of the solutions that we can all draw. Okay. So my problem is this. I have 20, sorry. So we have 15x1 plus 15x2 equals 400. x1 plus 2x equals to 40. Okay. Graphing says that we should first of all find out if the decision variables are 2. If they are 2, to plot the graph, let me say this is x1 and this is x2. I need coordinates. Whoever is talking, mute your, who is that? Eunice or Eugene? Eugene, mute. Okay. We need coordinates in order to plot the graph. So the assumption is that I need the coordinate for equation 1. I need the coordinate for equation what? 2. In order to arrive at this coordinate, I'll make some assumptions which are the underlying issues that we can use to solve problem. So if I pick equation 1 and I want the coordinate for x1 and x2, I will assume if x1 is 0, what should be x2 in this equation? It means that if x1 is 0, I'm left with what? 15x2 equals to what? 400. And for that matter, x2 will be what? It's going to be 400 divided by what? 15. Please, are you following? 400 divided by 15. Then if x2 is also 0, what will be x1? X1 will be equal to, just to say 20x1 equals to 400. X1 equals to 400 divided by what? 20. I hope that is clear. So
Yes,
it's
please.
just to say that I want to find the coordinate for the, in this case, this is 26.67. So this coordinate says that 0 and what? 26.6. This one too says that if x2 is 0, this coordinate will be what? This will give me 20 and what? 0. If I have this coordinate, I can now plot a straight line for this equation. I use the same assumption for this because I need the coordinates here. What that I do is if x1 is 0, x2 will be what? The same to say that 40 divided by what? 2. So x2 respectively. Then if x2 is also 0, what would be x1? Actually, x1, sorry, if x2 is 0, what is going to be x? So this will give me what? 20. It means that my coordinate here is 0, what? 20. If x2 is 0, x1 will be what? Again, in this equation, 40 divided by what? 1. X1 will be what? 40. This coordinate is what? 40 and what? 0. If I do this, then I can come and plot the graph. So please note that what I have here, oh, I don't need this. Okay. And in plotting the graph, remember you have negative and positive values. But if your the solution you have to the coordinates are all positive, you don't need to draw the entire negative and positive graphing that you have. So what I have here, let me just do this. We know this is 0. This should be this is my x1 and this is x2. Okay. Therefore, if I want to plot my graph, okay, if, sorry, this is x2 and this is x1, okay. What do I do? So x2, x1 is to pick this coordinate. When x1 is 0, let me say this is 10, 20, 30, and 40. Same 10, 20, 30, and 40. So if x1 is 0, means that I'm here. x2 is 26.67. Let's say that is somewhere here. Okay, so this is the point of intersection. Then in the same equation, if x1 is 20, x2 is 0, x2 is 0, x1 is what? 20. It's also here. I can now join these 2 points. And I know that this straight line is for this equation, 20x1 plus 15x2 equals to 400. Then the next coordinate says that when x1 is 0, x2 is 20, that's somewhere here. And when x2 is 0, x1 is 40, it's also somewhere here. I can now join the 2 together. Then as we said, this equation is x1 plus 2x2 equals to what? 40. All that we have done is to just draw the graph. Then if we do the graph, we are looking for the value for x1 and what? X2. Our solution is the point of intersection where x1 and x2 what? Meet. That's all we are looking at. So this is the point of intersection. Okay, if this is a point of intersection, let's say this comes down somewhere here, and this guy is somewhere here. Okay, can I agree? This could be 8 or 9. Okay, and this will be somewhere like 15 or 16. But the solution, when you draw, you should have 8 and what? 16. So in this case, we say that x1 is 6, 8, x2 is what? 16. And that is how we do the graphing system. Okay. So let's go back to, so graph, just to say that, first of all, identify the coordinates and plot or draw the straight line. And the point of intersection is where your solution is. We can have more than one, more than two equations. And by doing that, we use the graphing system. Please note, an inequality of form in this form means that we have this sign here correspond to half space, okay? So that if I plot the graph and it is less than or equal to, it means that if it is less than or equal to, I am just on the straight line or below the straight line, less than or equal to. If it is greater than or equal to, you are again on the straight line or above the straight line. So if this is the caveat, this first one, less than or equal to, and I draw my straight line here, we are saying less than means I'm on the straight line or below the straight line. That's half space. Then if the inequality sign is also greater than or equal to, in the equation that you are plotting, you are on the straight line or above what? The straight line. So that is the linear equation. So for inequality sign, we need to be mindful before we get our solution to the problem. And the solution to the problem when you are using the graphic system is called the feasible solution, okay? The feasible solution means that there are multiple solutions that you can get, but one of them will give you the answer that you seek. Because for each line that you draw, this could be the feasible solution area. This could also be the feasible solution area. That's why we said the point of intersection will give you the optimal solution that you are looking for. All right, so let's look at this example here quickly. This time around, we don't have equal to, but we have what? Less than or what? Equal to. So if I assume let x1 be 0, x2 will be what? 20. And if means that this coordinate is 0 and what? 20. And if x2 is also 0, x1 will be what? 300 divided by 20 should be what? 15. So this is 15 and 20. So I come here, when x1 is 0, somewhere here, x2 is what? 20. That's the. Then when x1 is 15, somewhere here, x2 is also what? 0. That gave us a straight line. The feasible solution on this or for this equation is that we are either going to find a solution on the straight line here or below the straight line. So where you have the shaded area, okay, is what we say the feasible solution area. But we are looking for just one solution, and that is called the optimal solution. So although you have a lot of feasible solution possible to give you x1 and x2, we are looking for the one that gives us the accurate solution that we are looking for, such that if we should substitute into the equation again, we should get the value of the resource that is given available. So given that a household has $350 to spend on rice and soda drink, and $35 to spend on transporting them to the house. If a bag of rice sells for $20, and it will cost us $1 to transport, that for soda drink is $15, it costs $2 to transport. Write the detailing how available money is spent on the items to plot. Again, you need to define your decision variable first. After you define the decision variable, then you go further to write what? The equation. So we have $350 and $35 to spend on to buy rice and to transport them. given what to be spent on each rice and how much to transport for the product, we define our decision variable as this. Let x1, x2 be the number of bags of rice and packs of soda drinks bought respectively. Then this becomes our equation. Remember, it's what? Available. What you have available to what? Spend. And we said available is represented mathematically as less than or what? Equal to. So 20x1 plus 15x2 is less than or equal to 350. x1 plus 2x2 is also what? This. So to plot it, this is where we have, this is our equation. We equate it to find the coordinate. When x1 is 0, x2 is what? 17.5. The coordinate here is 0, 17.5. When x2 is also 0, x1 is what? 35. So 35 and 0. This is for the first equation, this guy here, which gives me this straight line. This guy here, 17.5 is somewhere here. And that for, okay, this is what I'm looking for. Good. Then the next one says that 35 and what? 0. This is 35, 0. So I join these two lines, these 2 points to give me this. This is what I have here. Then the next one says, so if I plot this, my feasible solution area is telling you the shaded region, this, the possible areas I can get my solution. Sorry. Then for equation 2, when x1 is 0, x2 is what? When x2 is also 0, x1 is also what? So that should, that is what we are looking for, this one here. So we plot the graph respectively to give us this straight line, this guy here. Then that one is shaded in what? Blue, for that straight line. So where I have shaded, it means that I am on the line or below what? The line to get my solution. But though I may have possible solution, because we have 2 lines, my interest is the point of intersection somewhere here. So you realize that I have this guy here. The region that is common to both lines is this guy here, this one. These are the region common to both lines. Yes, David.
Sir, please, some of us have class right
Yes,
after
I know.
you.
I'm
So
going to
some
end the
4
class
minutes
very
away.
soon. I know. So we'll end the class here, but all I'm trying to say is that apart from the matrix, you can also use graphing system to solve your equation. And with graphing system, you can only use graphing system if you have 2 decision what? Variables. On that note, you have the recorded lecture, I'm sure in the course of the week, but we'll meet again on Wednesday to continue with our class. So thank you very much for your time today.
Thank you.
All right.
Thank you.
Have a great
Thank
week.
you, sir.
Thank you.
Thank you very much, sir. And
Thank
enjoy
you
your
very
day
much.
as well.
Enjoy your day, sir.
Thank you very much.